Hello everybody, I hope you are doing well. We are in the last week of the month of April, my birthday week. Thursday is my birthday, and on that note, we're going to have a very special Think Outside the Box Thursday, a birthday edition. It will also be our last Think Outside the Box Thursday of the year, so look for that on Thursday. I may post it tomorrow evening, you're watching this on Wednesday. Today I'm filming, it's Tuesday. Anyway, you may get it on Wednesday, but I'm working on a very special Think Outside the Box Thursday, birthday edition, our final Think Outside the Box Thursday of the year. Quick little running update, as I told y'all at the first of the month. I set a personal goal to get my Platinum 100-mile badge for the month of April. Again, today is Tuesday the 28th. As of right now, I have 93 miles logged for the month, so I have 2 days, and 7 miles to go. So I should be able to knock off my platinum badge Thursday morning. I hope you are all doing well. I hope you got the notification that they're working on some stuff for you seniors, graduation, and if I'm not mistaken, something about prom. Anyway, be watching for emails from Dr. Harris if you haven't already gotten some. I know there's going to be a drive-through graduation in May, scheduled right now, again, tentatively scheduled, and then a regular graduation ceremony later on in the summer. So hopefully those will be good opportunities for us to see each other again before we all go off out into the big world. You juniors, of course, I will see all of y'all next year, whether you're in my classes or not. I'll make sure I say hey to you in the hall. I hope you find today's lesson enjoyable. Thank you. So today's lesson is starting chapter 7, which is on linear momentum and collision. Actually fairly easy chapter. I don't think most of the stuff in momentum and collision is pretty straightforward. I don't think anybody's going to have any trouble with it that's looking at this. You can see from the chapter contents, we have 4 different parts: momentum, impulse. Those are the 2 things we're going to talk about today. You've already seen one video on those, which introduced them to you. So hopefully you'll find today just as kind of a refresher what you've already seen. Next week we'll talk about conservation of momentum and then the different types of collision. Probably the hardest part of the entire chapter is going to be the discussion of collisions and what makes a collision elastic or inelastic, and so that's something we'll be doing next week. And we'll actually have our third lab that we're going to show is a collision lab, which is a really good one. I hate that you'll have to miss that one, but we'll be looking at that next week. The definition of momentum, again, I always consider momentum to be basically common sense physics, because if you look at the pictures here, on the left, we've got a girl throwing a ball at the boy. It's a big ball. You'll notice from the line of the vector for the velocity of the ball, we have a big ball going slow, hits the boy, and it makes him move backwards slowly. Well, the picture on the right has a boy throwing a smaller ball at the boy, and you'll notice its vector, it's much longer, so it's going fast. That's basically momentum in a nutshell. Momentum is mass times velocity. So if you take a large object going really slow or a tiny object going really fast, they can have the exact same momentum. I mean, if I could throw this baseball fast enough, I could stop a tractor trailer from moving. Again, assuming that the baseball is hard enough and the tractor trailer is hard enough that it wouldn't just pass through the tractor trailer or it wouldn't disintegrate on impact. But if it was just pure collision, the ball hits it, the ball could move fast enough to cause a tractor trailer going at any speed to stop, because all we have to do is balance out its momentum, because momentum is mass times velocity. If this is going fast enough, it can stop virtually anything. The symbol for momentum is P, so make sure you're careful when you look at the formula there that the symbol for momentum is P. And the momentum that we're going to be talking about in this chapter is linear momentum. Now there is also angular momentum, which we'll talk about. I've got to check the schedule either next week or the week after. Angular momentum, remember, velocity can occur whether you're going straight and you change your speed, or if you change your direction. So you can have what's called angular momentum if you have something going around in a circle. So it's a little bit harder topic, but just realize for this chapter, everything we're doing is linear momentum. Momentum, very quickly, is a vector quantity, so we can draw arrows to represent it. And if you take a look at this example, a fairly classic example of momentum. We have two objects. We have a beanbag bear and we have a ball. The beanbag bear and the ball both have a mass of 1 kilogram. And the top picture, they're both moving down with a velocity of -4 meters a second. Well, after the beanbag bear strikes the ground, its velocity becomes 0. When the ball strikes the ground, it has a perfectly elastic collision, and it bounces up going 4 meters a second. Well, if we were to calculate the change in momentum for both of these systems, you can see on the next slide that for the beanbag bear, the top one, we end up with a momentum final is going to be 0 because it's not moving. Anytime an object is not moving, it has no momentum. And the initial momentum is -4 kilogram meters per second. Kilogram meters per second, I didn't mention that before, that's the unit for, kilogram meters per second is the unit for momentum. But if you take a look at the rubber ball, final momentum, since it's going up +4 meters a second, positive 4 meters a second, ended up with a final momentum of 4 kilogram meters per second. And its initial momentum was -4 kilogram meters a second. So when we do final minus initial, we end up with 4 minus -4, which gives us a +8 kilogram meters per second. So momentum, as you can see, when you look at a problem like this, because the bear stops, its momentum is dissipated, its change in momentum is 4, whereas bouncing a rubber ball off the ground, its change in momentum is 8. Don't get freaked out by the numbers there. Impulse. Impulse is what you get when you apply a force over an object for a certain amount of time. Now, force is in newtons. Well, a newton is a kilogram meter per second squared. Well, if I take kilogram meters per second squared times seconds, the seconds will reduce with the second squared, and I end up with kilogram meters a second. Well, kilogram meters a second is mass times velocity, which is momentum. So again, as I said before, momentum and impulse are exactly what you would expect them to be. If this ball is sitting here and I apply a force to it, I'm going to make it move. The more force I apply to it, the faster it's going to move. Boom, boom, boom. That is called impulse. I'm applying a force over a time interval. Impulse is force over a time interval. The momentum is what you get when something is already moving. So if this ball is rolling along here, its momentum is defined by its mass times its velocity. So I can change the momentum of an object by applying an impulse to it. Or I can cause the momentum of an object to stop if it's rolling this way. If I apply a force in the opposite direction, I would be giving it a negative impulse, and therefore I can cause an object to stop moving by applying an impulse to it. The impulse is the force that you apply over a time interval, where momentum is just the mass moving at a certain velocity. It's really, really, really easy once you see a couple problems, which you're going to see today. I'm going to leave you with this example, and this will be a bonus question on your video acknowledgement form. So if you will answer this problem, you'll get a 5-point bonus. Remember, every time you're turning something in, the only thing that can happen to your average is your average can go up. So I hope you found today informative, and I hope you don't have any problem with the example problems that I've given you to work today. Thank you.